I might have touched on this in a previous video, I'm not sure. But I don't know, I've kind of been wanting for a few days to do a video about kind of my interpretation of what general relativity means. And I'm probably gonna fuck it up here because, yeah, it's weird. It's complicated enough that I get lost in my explanation of it. Um, yeah, so there's this relatively minor issue in physics. Minor because most people don't actually doing physics don't actually care that much, but it is a problem. Definitely gets blown way more out of proportion in the public sphere because it involves Einstein and quantum mechanics and like the big popular sorts of things, right? Einstein being involved because of general relativity. Right, so you got the problem with like gravity and uh, the other interactions don't seem to be commensurate in any sort of way. Where like electro, the electroweak forces, the electroweak interaction, right? So you've got electricity, magnetism, and the weak nuclear force. They unify, but also they behave quantum mechanically. And then you have the strong nuclear force, which also behaves quantum mechanically. But then you have gravity, which doesn't seem to behave quantum mechanically, so they don't seem to mesh. One of the problems that I have with the way that this is brought up is a lot of times very early in analyzing this, um, the fact that gravity is massively weaker than electricity, the other forces, all of the forces, but particularly electromagnetism, is brought that comes up. That's brought up. Um, okay, so for us in our daily lives, that is a fact. That is true. We are made out of stuff that is able to hold itself together and also not be crushed by gravity due to its electromagnetic properties. But that doesn't mean that gravity is weaker than electromagnetism or the electroweak force. All that it means is that for the crap that we're made out of, those things interact much more with in the electromagnetic interaction than they do when the gravitational interaction. That's all that actually means. And for substances like dark matter, very much the opposite is true. So, you know, if you were a scientist made of dark matter, and your world was made of dark matter, and you existed, in this dark matter sort of realm, I suppose, because it's sort of mysterious to us and we can't understand it, so it's kind of like a completely alien sort of thing. So, hypothetically, say you were this sort of a person, your conclusion would be that gravity is by far the most powerful interaction there is. For you, that would be the fact. So, I'm taking issue with this idea that, yeah, gravity is weak, and we need to account for that weakness somehow. Like, oh, maybe there's other dimensions that it's just like curled up in some weird fucking way, like. Or maybe you're biased in some stupid way that you don't understand, dipshit. Somehow, that has never fucking occurred to anybody. Like, oh, maybe it's just because the shit that we're measuring doesn't really interact very strongly with gravity. Maybe that's all it is. I've never seen that argument posed. Like, what the fuck? That should be the first most obvious argument anybody makes. Right? Like, if you're sitting here trying to rigorously understand stuff, and it's clear that you have things that don't interact in all of the interactions, like neutrinos, which are electromagnetically neutral. That's why they're called new fucking trinos. They don't interact with that. Well, then there's probably stuff that doesn't interact with gravity. There's probably stuff that doesn't. But you know what? We haven't found anything that doesn't interact with gravity. You know what that tells me? That tells me that we're probably missing some shit. We got stuff that doesn't interact with the strong nuclear force. We got stuff that doesn't interact with the weak nuclear force. We've got stuff that doesn't work with interact with electromagnetism. But we don't have anything that doesn't interact with gravity. That means we're missing something. That's what that tells me. Instantly, that tells me that. Instantly. My entire life, that's been knowable. My entire life, that should have been a conclusion that somebody had drawn prior to me. Nobody seems to have drawn that conclusion. I've never seen that published. Granted, I haven't read absolutely every publication in like theoretical physics and shit, but fucking I don't think anybody could. There's too many at this point. But the fact that I've never like even remotely heard rumblings of anything like this is probably indicative that it's at least not a sort of major thing that anybody takes seriously. So I have a problem with that. That seems insane to me. Like, why are you overlooking something so fucking obvious? Especially when you already have something that is proposed that you've taken measurements of, where it has extremely little to no interaction with electromagnetism, but definitely interacts gravitationally. We know of something that behaves in this way. What the fuck? Why are you going around still saying that gravity is much weaker than electromagnetism? Right? And the experiments, right? The experiments that verify this, right? You just take something and you drop it on the ground, and you're like, oh, look how long it takes for it to accelerate to this speed, and look how much distance it takes for it to stop. Right? That acceleration, that's due to gravity, and that requires the entire mass of the Earth. But that acceleration, that's due to electromagnetism, and it really just takes, fuck all to make it stop. Yeah, because the things that are interacting here are made out of shit that interact much more in the electromagnetic interaction than they do in the gravitational interaction. Okay? So that's kind of my first problem. And I think that's very easy to understand. It's simple, right? I have other issues that they get kind of weirder. I don't know. This is in no particular order, so we might come up with one that's easier. And I'll probably forget some of my points too as I go along, because there's enough of them that I get lost. But anyway, so there's that. Claiming that gravity is weak. Yeah. Okay. So now, kind of taking the sorts of things that we know about these other things, like electromagnetism, Higgs, all that bullshit, right? They have fields. There's fields. And they permeate space. They permeate, right? There's just an electromagnetic field everywhere. And when two things are attracted to each other or repulsed from each other electromagnetically, they're not beaming quanta of the electromagnetic interaction. They're not like interacting with quanta of the electromagnetic interaction. What they're doing is they're interacting via the field itself. Right? So there's any energy required to make this happen is coming from the field. Right? That's basically That's the gist of how that works, or at least how that's explained, how that's justified. Right? So two things are coming together. The energy required to accelerate those objects is coming from the electromagnetic field, which permeates space. It's everywhere all the time. Right? There is no piece. You cannot have a parcel of space that doesn't have electromagnetic field in it. Just like you can't have a parcel of space that doesn't have Higgs in it. And you can't have a parcel of space that doesn't have gravity in it. So now we just hit on something. The field for gravity, I think, is space-time. That's what general relativity discusses. That's what it's describing. It's describing the behavior of the field. But the problem is, because of the way that I think Einstein was thinking about it, I'm not even sure if he was actually thinking about it this way. It is definitely understood that he was thinking about it this way. But it's a simple fact that you can't control how people understand the shit that you say. Right? You can say something with a particular meaning, and maybe nobody ever understands what you said, or like what you meant, right? They take what you said and they get a different meaning out of it. And particularly with shit that goes viral, that tends to be what happened. So I'm totally willing to give Mr. Einstein the benefit of the doubt and say, yeah, he might not have been this stupid. I mean, he certainly wasn't a stupid guy, but everybody makes mistakes. Everybody's stupid in certain ways. But it's not a judgment. It's just how it is. I am absolutely stupid most of the time. Whatever. Stop freaking out. Okay, so space-time, I think, is just the field of gravity. Which means that it permeates space. Which means it's not space. The problem is, space-time is taken to be space by fucking everybody. Except that it isn't. Because you can't take it that way. And use the math of general relativity. And this is really, really prominent in something that was recently confirmed to be real. Gravitational waves. So, fucking hell. Alright. Going back to kind of the basic geometric principles. Right, you've got this idea of curvature. Right, so, like, fucking some cloth or something, right? You can curve it. Woo! Look, it bends. Alright, so say we have this is flatland. This is two-dimensional flatland, and we have these little guys that are going around. Yeah, I'm pretending to be gay because this is a fucking gay piece of shit story that I know you've all seen before. So, okay, you got the flatland things, and if you put intrinsic curvature into the thing, then they can detect it, right? So it's like, you have little, just use my face because it actually has curvature in it. It has real curvature in it, whereas this is flat. This is actually flat, and all I'm doing is bending it. That doesn't do shit. You can't detect that as a flatlander. However, if you're a flatlander on my skin, you can actually detect, like, what's happening right here. Where's the camera? What's happening right here, right? As you come down, it seems pretty flat. It seems pretty flat. And then suddenly, it's really sharply curved right here. And then over here, it's really sharply curved. Over here, it's really sharply curved. It's around here, it's much more sharply curved than it is over here. Alright? Like, my ears, there's all kinds of crazy curves happening. Right? So something moving on this, it's going to feel distortions. It's going to feel that. A detectable distortion like this is called intrinsic curvature. Right? It's a curve inside the space. Inside the... So here it would be a two space. There's two dimensions. We live in a three-dimensional space. So for us, detectable curvatures would be things that distort right? So maybe say you're traveling in a straight line, but there's a planet or some shit, and you come near it and it curves your trajectory, right? We know that this happens. That's what orbits are of planets. You got the sun and you've got things curving around it. You've got the Earth and you've got the moon curving around it. You've got the space shuttle curving around the Earth, and that kind of bullshit, right? That's the idea. That's the idea that Einstein had. He's like, it's just geometric. And that's totally fine. Problem is, you can't have intrinsic curvature without its opposite, extrinsic curvature. Extrinsic curvature is this, right? It's when I'm doing this shit. If you notice, my face, the intrinsic curvature on this two-dimensional surface, it all corresponds to an extrinsic curve as well. It's also curved in 3-space. The 2-space has distortions because of the way that it's curved in 3-space. Right? So, like, there's a line right here where you can say, yeah, that's flat, at least in this direction. It's more or less flat, kind of in this region here. So this is purely an extrinsic curve, right? You can basically model this as like a cylinder, this little band right here. Pretty close to a cylinder. So there's basically no intrinsic curvature there. Okay. And there's basically no intrinsic curvature just crossing here. But once you get like here, up by my eye, up here, you're definitely running into intrinsic curvature. But you're also running into more extrinsic curvature. You can't separate the two. As far as I can tell, I've never seen an argument where you can actually have intrinsic curvature without extrinsic curvature. I don't know how that makes sense. I don't know how you can get that. I don't know. You probably can. I don't know. Math is fucking weird. But I've never seen anybody actually even try to argue this. What I have seen is people say, no, it's intrinsic. Talking about curvature in space-time. Like, what? That means there's an extrinsic curvature as well. And then the argument, like, they don't understand what I'm saying, and it just turns into bullshit. So, I'm just putting it out there right now. I have never seen an argument demonstrating that you can have intrinsic curvature without extrinsic curvature. So claiming that it's just intrinsic is bullshit, as far as I can tell. Now, I could be wrong. Intrinsic curvature could be possible without extrinsic curvature, as far, whatever. I just don't know about it. Right? I'm just one person. The universe is not accountable to me. Whatever. Okay? But, as far as I can tell, intrinsic curvature implies extrinsic curvature. Now, you've got this problem where if space-time is just the field of gravity, then it's just something that permeates space, so it's distinct from space. You have this problem if we're proposing this. But it's actually not a problem, because say we're looking at gravitational waves. Okay. The way that this is supposed to work is a gravitational wave passes, and what it does is, so we've got our two, like, our measuring devices, right? They're shooting light back and forth at each other, or whatever. However you want to do this, we're shooting light. Let's just say, say we've got a laser beam and a detector, and we know when the laser beam is firing. It's just firing pulses. It's on this hand. We're just firing pulses, and we've got a detector over here, and we know when to expect the pulses. Very, very precisely, we know when to expect the pulses. To the best of my knowledge, this is roughly how, like, fucking LEGO works. Now, the gravitational wave comes along, and it alters the distance between these two things. Okay. Now, this is where I have a problem. I don't have a problem with that. Where I have a problem with is when it is claimed that that alters the time and that it's purely intrinsic. Because how could it possibly alter the time if it was purely intrinsic? Because what would happen, we've got this little back and forth thing going on with the gravitational wave. It's affecting all of the matter, right? It's affecting all of the matter. So we've got this light beam coming across here, and it is unaffected somehow by this gravitational wave. How? How is the light unaffected by the gravitational wave? We know light is actually affected by gravity. We know this. So it actually should not get a get out of free jail card here. We know that light should be subject to the influences of gravity. Because really, what appears to be the case is that the charge of gravity, gravitational charge, what that is energy. Energy is gravitational charge. So the quantum of gravity was whatever the smallest amount of energy you could ever have. That's what it would be, I think. Maybe. Something like that. Because it's not mass. It can't be mass. It can't be. Because if it were mass, then light would not be affected by it. You couldn't have black holes. But light is affected by it, and you can have black holes. And you can have gravitational lensing and all kinds of other crazy shit. Because energy is what gravity affects. And it turns out when you actually set up your units right, energy and mass look the same. They look like the same thing. So, yeah. I know I've mentioned this before in a previous video. Anyway, yeah, so the light energy should be feeling these ripples as well. So when everything is contracting, the light should actually it should come back towards the transmitter, right? Say, right, we've got our laser pulsing, we've got our detector, and as long as the light is still in that first half, when it contracts, it should be getting closer. And when it should be doing that. And the light should be moving back and forth relative to this. They should both be moving. Just like the detector, right? Like, that should be happening. That should be happening. And it should be happening in such a way that if it were purely intrinsic, should be happening such that the time doesn't change. It should be happening in a way where the gravitational wave isn't even measurable. But the wave is measurable, which means that it's actually density, it's gravitational field density, that is what is changing. And it is changing within space. So space-time, which is the gravitational field, is the thing where the tensors. That's what that's talking about. It's basically the amount of charge in the field at any given point. But space is still space, no matter what, right? Then the relativistic effects come about because we're fucking made of shit that's subject to all of these effects that come from disturbing or altering charge in the gravitational field in space-time. That's why we can't measure space. We can't. Because we're built out of shit that is really integral to, like, tied to the electromagnetic fields and the gravitational fields. It's like how that shit happens, right? So we can't really see beyond that. Like, we're subject to effects. So you get the relativities. And it's sort of my interpretation of how space-time works. So what's going on there is time. The time that we're talking about here, it's not time, big time, like some grand, all-encompassing time. It's clearly not that. It's because it's relative, right? So, like, two things traveling at different speeds relative to each other experience time differently, right? There is no grand, as far as can be measured, there is no grand time. That can't happen. Fine. I'm totally fine with that. The reason for this, I think, my interpretation, is that, and I don't think this is actually heretical. I don't think this is contentious in any way. Right, so the speed of light is the maximum speed limit. Right, that's as fast as you can go. Ish. We'll just say it's as fast as you can go. It's the speed limit. Okay, cannot go faster than the speed of light, especially if you have mass. Okay, so it is the rate of interactions. That's what it actually is. It is the speed the speed of light is the speed of interactions. Okay. It is, but it is also really the only thing that you can base time measurement on. So even Einstein's thought experiment, where he's got the light clock, like, you can see this coming into play. Like, it's not actually affecting the material, it's affecting the rate of interaction between the particles in the material. Right, so we've got, in order for your finger to stay together, the things that the particles that make up your finger have to talk to each other, and they have to share electrons, and they have to, they have to do shit. They have to interact with each other. If you are moving at close to the speed of light, basically, so say we're going that direction at close to the speed of light, this particle back here, sending, just doing its thing, just broadcasting, basically, its broadcasts almost never ever reach this. It takes for fucking ever, because we're going so close to the propagation speed of the information from here that it's going to take ages, even though we're, like, down at the molecular level. We're, fuck all. These things are, I'm representing atoms. Say this is, like, maybe nitrogen, dinitrogen or dihydrogen or some shit like that, right? This bond between these things sort of breaks. It sort of disappears at close to the speed of light when, the direction of motion is going through both atoms. Because this atom at the back is never able to talk to the atom at the front, and the atom at the front is never able to talk to the atom. They're not able to talk to each other at the speed of light. So it basically just ceases to be material. And, like, the internal components, the quarks making up the protons and the neutrons and the electrons, like, none of these pieces can really talk to each other anymore. They just kind of become frozen in an arrangement. And thus, time, as far as it is concerned, doesn't happen. It doesn't pass. But this does require an overarching time, a universal time, that's inaccessible to measurement. And I think this is what the problem is. Because if you can't measure it, then we want to say it's not real. But this overarching space that everything is embedded in is real. It's like you can see it in the math. It has to be real. In order for a curve to make sense, you have to have a plane. You have to have a Euclidean geometry for the curve to be in. You just have to. That's how the numbers are working. They automatically are giving you this Euclidean space. Right, so I've always thought it was really strange, like this talking about non-Euclidean geometry. It was like, but all geometry is embedded in a Euclidean space automatically by virtue of using math. You cannot escape it. What the fuck are you talking about? I don't understand. Where was I going with this? I told you I would get lost at some point. Yeah. Okay, so you have to have this overarching time, and you have to have this overarching space. So space-time is not actually space or time. What it is, okay, so we kind of got into the time thing. So what the time part of space-time is the rate of interaction between the components of a system, right? So say you have some reference frame. Well, but it's a reference frame of energy, stuff made of energy. And stuff made of energy can only interact with it, this little packet of energy can only interact with this packet of energy at the speed of light. So if they're traveling at the speed of light, they'll never interact with each other. So between them, you never get time passaging. You passing. You never get an interaction between them, so time doesn't happen. Right. That is predicted exactly. The details of that. If you look at the world that way, the mathematics of that is exactly the mathematics of general relativity. It's exactly the same thing. The way that it behaves is exactly general relativity. And I think looking at Einstein's work, looking at how he was talking about it, I suspect he was thinking about it in, if not that way exactly, similar sorts of ways, because he was using things like the hypothetical time clock or light clock and things like this. Like, you're basically looking at it that same way. You're just looking at it at a larger scale where you could actually build a device. But it's basically like, yeah, the rate of interaction between these two mirrors with this light beam is the speed of light. And at the speed of light, basically, you can't measure time anymore because the light can never bounce between them. We're at a point where that can't happen. It's just, we're done. We're done. Time doesn't you can't measure time anymore. So that's what it is. It's measurable time. It's not time. It's measurable time. So this has some consequences, because it means that warping space-time never ever means that you can go back in time. And it never ever means that you can go into the future. That's not what this time is. This time, the time that is space-time, is measurable passage of time. Basically, there's two things that this predicts. You can freeze something in time, right? You shoot it off at the speed of light. It's stuck. It doesn't age. Okay. But then there's another side of this, which is if you stop something, if you stop, take it, some object, some reference frame, stop it in space, it will actually age faster than everything else around it. Which means you can actually find the speed of the universe, like the speed of a parcel of space. You can in that way get to basically if you did it just right. And I don't think this is, I'm not even sure this is actually possible, but sort of hypothetically, like in an ideal world where we're ignoring real shit, because accelerations fuck up time. So yeah, you end up with that. Yeah. So if you could stop something in the space that's around it, so it's not moving at all, it will experience time faster. That's what this means. So you can kind of, in that way, you can sort of get to the big time. The time that, the passage of time that affects, that kind of runs the show. I don't think this is going to be very interesting because probably for the most part, most objects naturally occurring in space that aren't shit like photons and neutrinos, like the solar system, things like that, are probably really close to this speed anyway. So, eh, the difference might not even be measurable, and it's certainly not going to matter very much. Like over human lifetimes, like it's not going to fucking matter. But it is an implication that I've never seen anybody note before. The inverse of this implication I have seen noted, but I've not seen it noted the way I'm going to explain it. I've seen it noted close to the way I'm going to explain it. But, so basically, we have, we know that objects very far away from us can actually travel away from us at faster than the speed of light. And the reason for this is that parcels of space aren't subject to this restriction. The speed of light only operates within a parcel of space. But two parcels of space, the opposite ends of them, like this parcel of space is growing and this parcel of space is growing, and if they're growing fast enough, then things at the opposite ends of them, without moving relative to the space around them, can actually recede from each other at the speed of light, or at 10 times the speed of light, or any fucking speed, right? So what this means is you can actually launch from a location at half the speed of light, and after a little while, you actually stop moving relative to the space around you. Like, asymptotically, you stop moving relative to the space around you. So, basically, no matter how fast you're launched, right? You just get like an initial kick. No matter how fast you're launched, eventually you'll just stop relative to the space around you. Unless you're something like light, which is propagating. So light will propagate at the speed of light forever. It's always operating at the speed of light for the parcel of space that it's in. But you getting kicked out will eventually stop. That's interesting. You have to go a long ass fucking distance for this effect to take over, because neutrinos from fucking stupid distances are still relative to us moving at damn near the speed of light, and they started off at damn near the speed of light because they have mass. They can't be at the speed of light, so yeah, like this is not a big effect, but it is an effect. Yeah, so sort of like you can continue accelerating forever and stay at the same speed, weirdly, I think. I might be misinterpreting that. The universe might actually, like, as you're moving, it's just like, okay, and it just kind of keeps kicking you along for some reason, but that seems weird. It might do that. I don't know. That seems weird to me. Maybe. I don't know. Yeah. But anyway, I'm sure I'm wrong about 10 things here. Probably. It doesn't matter because nobody watches this shit. It doesn't matter. It doesn't matter if I'm right or wrong. Right? The truth doesn't care about me. The truth doesn't care about you. The truth doesn't care about anybody. It doesn't matter. I'm just putting out my ideas. Anyway, so yeah, I think if we look at space-time as the gravitational field, we look at energy as sort of the charge of that, then stuff starts making a lot more sense. Because basically what happens is the intrinsic curvature of space-time, well, it has an extrinsic correlate now, because space-time, the dimensions of space-time, are actually orthogonal to the dimensions of space, because it is a field that permeates space. Its properties are not properties of space, they're properties of itself. They're properties of that are distinct. So alterations to the properties don't alter the properties of space. So the dimensions of space-time are orthogonal to the dimensions of space. And thus you can get what effectively looks like a higher dimensional universe without actually having a higher number of dimensions of space. Right? You can have a 3 space that feels like it's got more dimensions to it than that, because, well, how do you explain the curvature that we're seeing in space-time? Well, it's just density of the gravitational field within space. That's all it is. But because we're made of energy, and energy is perhaps the quantum of gravity? I don't know. Something like that. It's all subject. It feels all of that. So the space, as far as we can see it, because of what we're made of, looks like it's curved. But really, that's not space. That's not a curve in space. That's a curve in space-time. It's kind of like on an old CRT television or computer screen, right, where you would have adjustments that yeah, I think you still get it on like projectors and shit. Right, you can kind of change like how the electron beam is scanning onto the CRT, onto the phosphorus. You can control, you can warp it a little bit. You can get it to go narrow, you can get it to go higher, you can get it to twist, you can get it to like one side scrunches. You can do all these effects. You can put a magnet up to it and it just goes all fucking wonky. But the information in the signal, right? Like which pixel is next to which pixel, never changes. It's like that. It's like that. You have the geometry of the screen itself is one of the things, either space or space-time. And the geometry of the image projected onto it is the other one. Right? So like here I would prefer to say like the screen itself is space. It's the thing that basically we can't affect. Right? Because we're pixels that are created by the electron beam. And gravity is like, gravitational effects are effects on the electron beam. Right? Like sticking a big magnet on the side of a CRT screen. Like everything is fucking just like bonkers, right? But as far as the signal goes, like nothing really changed. But the way that the image looks on the screen, shit changed. It's kind of like that. It's kind of like that. Yeah. And like we talk about electromagnetism in that way, sort of. Like, I don't think anybody explains it in exactly that way, but that's sort of the way that it's looked at. Like, yeah, you get these, like, there's more electric field here, and there's less out here. So electrons are attracted to, like, they follow this path to get to the, shit like that. It's the same thing. It's the same exact thing. Like, I don't understand why this is confusing. Why is this hard? Like, okay, yeah, we haven't found the quantum of gravity. But I think you can think it through and get at a pretty good fucking idea of what it would sort of look like. Gravitational charge isn't mass, it's energy. If it were mass, then light wouldn't be subject to gravity. But light is subject to gravity, so it's energy. That's it. That's it. It's not that fucking hard. I don't know. I don't know if this wasn't worth it. Don't watch my videos. Don't watch my videos. They're trash. Oh, yeah.